This is gases video number 6. By the end of this video, you should be able to solve problems using the combined gas law, Boyle's law, Charles' law, and gay-Lussac's law. In order to do this, you should have your gases video number 6 worksheet, a pencil, and a calculator. In the past, we've been using PV equals nRT. This is our ideal gas law. We're going to rearrange it in order to derive new formulas that we can use. Our first step, we want to solve for the number of moles. To solve for the number of moles, I'm going to divide both sides by RT so that I get N by itself. In this case, PV over RT equals N. Now let's consider having a sample of a gas. And if we have a sample of a gas and it's trapped in a container so it can't get out, then the number of moles that we have is going to be a constant. In this case, we can have more than one condition that makes this be a true statement. Maybe we have original conditions such as these that gives us our number of moles. But then we change the conditions, the pressure, the volume, and the temperature, which you're going to call P2, V2, and T2. Those are the new conditions. And they're also equal to N. As long as N and N are the same, then this is going to equal to this. Now notice R. I have not been putting out R as R1 and R2. And the reason why is this. R is the gas constant. It doesn't change. Since it's exactly the same on both sides, it's going to cancel out. So I can get rid of it. And what I have as a result is this formula. This is called the combined gas law. It is used for finding variables under changing conditions. As in every other problem we've done in the past, we want to make sure the units match. So I don't care if volume is done in liters or milliliters or cubic centimeters, as long as it match. The one thing I am concerned about is that the temperature must be in Kelvin. So whenever you see one of these types of problems, you should immediately take the Celsius and convert that to Kelvin. Now there's more that we can do with this formula than what we've just shown. For example, let's say the temperature is constant. If the temperature is constant, then it's exactly the same on both sides. I can cancel that out. And I get the formula P1 V1 equals P2 V2. This has a special name called Boyle's law. In this case, when the pressure goes up, the volume goes down in order to keep this to be a true statement. This is called an inverse relationship. And in this case, when the pressure goes up, we want to keep in mind that our volume is going down. Let's try the next case. In the next case, we're going to have a constant pressure. If the pressure is constant, and therefore it looks exactly the same on both sides, it also can cancel out. I get V1 over T1 equals V2 over T2. This is going to work as long as my number of moles and my pressure is a constant. This one, my number of moles and my temperature is a constant. Once again, I don't care what units I have, but T, it has to be in Kelvin. This relationship also has a special name. This relationship, though, is not inverse. It's going to be a direct proportionality, and as a result, if volume goes up, so does the temperature. Okay, last scenario. If the volume is kept constant, then it is also the same on both sides, and I can cancel it out. So that P1 over T1 equals P2 over T2. Once again, temperature must be in Kelvin, and it also has a special name. And just like before, this kind of relationship is direct, so that if one variable goes up, so does the other one. Oops, sorry, in this case it's pressure though. Okay, let's try our first example problem. In our first example problem, a gas has a volume of 14.5 liters at a pressure 725 torr. What is the pressure if the volume is increased to 20? So P1 is going to be 725 torr. V1, under the same conditions, is 14.5 liters. P2 is what we're trying to find out, and V2 is 20 liters. Now you want to take a look and see which formula is the correct one in this case. Since we have pressure and volume changing, and we can assume that T and N are constant, then we're going to use P1 V1 equals P2 V2, or the gas law constant, that's Boyle's law. Let's go ahead and put down the formula we're going to use. Okay, we're solving for P2, so I'm going to divide both sides by V2 so that I can get P2 by itself. Now I'm ready to plug this in. And as we can see, the liters will cancel because we have matching units. 725 times 14.5 divided by 20 gives us a total of 526 torrs, because that's what our pressure units are in. Go ahead, stop the video, try example number 1 and 2, then check your work. Okay, in number 2, we also want to list our units. Since we have pressure and temperature changing, we're going to use the formula P1 over T1 equals P2 over T2. Getting P2 by itself, I'm going to multiply both sides by T2. So that what I get now is T2 P1 over T1 equals P2. Let's go ahead and plug it in now. Now, going back and taking a look, we have Celsius and Celsius, and we know this only works in Kelvin. So I'm going to add 273 to both of these to get 297.8 Kelvin, and on the other side, 286.2 Kelvin. And when I'm done, 286.2 times 1.15 divided by 297.8, Kelvins have canceled, I get a total of 1.11 ATM. Now you want to double check and make sure this makes sense. Remember, this is a direct relationship. If the temperature goes down, I expect the pressure to go down as well. And it did, from 1.15 to 1.11. Let's try number 3. You should already have number 3 done, so you can double check your work. I'm going to list my units on the side. Notice in this case I have pressure, volume, and temperature all changing. I like to list them on one side and then the other side so I can easily compare my units. By doing so at this point in time, I notice I don't have matching units, and I will have to stop and convert before I can proceed. Okay, 735. 735 mmHg. Drop down the mmHg, ATM on the top, and it's 760 mmHg equals 1 ATM. So I get 0.967 ATM. Now my pressure units match. They're both in ATM and I can do the problem. My volume units are both in milliliters. That's fine. And my temperature was given in Kelvin, which is what I want to use. Write down your formula. And then let's rearrange the variables. I'm going to cross multiply. Then I'm going to divide both sides by P1V1 so I can get T2 by itself. Okay, let's go ahead and do our plug-in now. Plugging in with our units. And you can see how the units are going to end up canceling each other out, the ATMs and the milliliters, and you'll have an answer left in Kelvin. So I'm going to do 1.20 times by 525 times by 298 divided by the 0.967 divided by the 634. I do that without any kind of parentheses, and I get 306 kelvins for my final answer.